Okay. It's weird. Okay, there we go. All right, everybody can see the screen and everything. All right, let me put all of my people up here. No, still. It is actually funny. All the faculty meetings and other meetings I go to, everybody has their camera on. Like if somebody doesn't have the camera on, they're like asked to turn it on. And I think part of it is A, it makes it seem more like, you know, real class, but also B, you can tell when somebody's paying attention and not paying attention, or at least easier. You know, like for all we know right now, you know, Francisco's nowhere near his computer, right? You know, he's just out. He probably is. He doesn't even know that we're talking to him. He joined. He's just there. Oh, well, I saw toilet paper. He's sitting on the stockpile. I hit the well, I mean, I'm not supportive of this, but I was at Meijer yesterday. Was it yesterday? Yeah, shopping. And they had just gotten a new shipment of toilet paper in. So it shocks me how expensive toilet paper is. Like because I don't buy it. I couldn't believe like this thing of toilet paper was like $25. It doesn't make any sense to me. That's all.
No one's buying the toilet paper used for like businesses. They're just buying the stuff that you buy at like Walmart. You know what I mean?
But like,
well, the thing is, why buy toilet paper when you can just buy a pillowcase and that'll work just as well?
Reuse it. Well, what I'm getting at here, not going down the pillowcase route since we're already recording. what I'm getting at here is that on Amazon you can buy the bidet things that I've been using for years for like $30. One supply of toilet. I don't even know how long that's going to last. My wife, is that like a 2-day supply? I don't know. I don't know what people are doing with this stuff, but I don't know. It just seems to be so much more cost effective to get a bidet, and it's now it's really funny that all these folks are. Oh, there's my chat thing up there. You know that. For years, I've been talking about them, you know, the ones I use when I travel and the one I have at home, and, you know, that they're cheap. Don't even buy the electronic fancy schmancy ones. Just get the normal cold water, whatever one. And now you're seeing like Time Magazine articles on this topic, and how Americans are finally going to embrace the bidet and things like that. So I don't know. Maybe that'll be the positive that comes out of this negative thing. Let's see. Everyone's pictures are covering the screen. Oh, so if you, or can I move this down here? If you see the screen here, in the upper left-hand corner, there's a little, that's like minimizing it. So you can do that, or you can only do the show active speaker video. So I'm on, you know, I have multiple screens, so I just shove it north. So that's why, you know, right now I'm looking up at everybody.
I was talking about the YouTube recordings.
Like my recordings?
Yes.
Well, you don't see my screen right now, do you?
I see the Mac screen.
Yeah, right. So, I mean, the YouTube recording would have just my Mac screen, wouldn't it?
Right, but for some reason on YouTube, there's, like, the left side of the screen is covered with everyone's profile pictures.
Really?
Yeah.
Like, even like this, if I'm recording right like this, is the YouTube shows everybody's profile pictures on the side of the screen?
Yeah, or the right side of the screen.
Yeah, so it would probably show kind of like this thing.
Yeah, there's a big box of profile pictures like look in here.
Look at what I have on my screen. Does it look like this?
I don't see anything on the screen right now.
Oh, you can't see the pictures. So like on the right side of my screen where you just drew that box right now, I see me at the top, then I see you, and then I see Luke. You don't see that on your screen?
Correct. That's not coming through on Zoom, but I guess YouTube is capturing it.
See, that's interesting that because the reason I say that is, I move it up so it's off the screen, where if I left it here, I might be able to see you guys a little bit better, but I move it to my top screen, and then I put it on grid so I can see everybody at once, thinking that now over here on the right-hand side, you would get to see, where it says blank and all that stuff. And right now you can see that. But what you're telling me is if you were watching this on YouTube, you would see where you wouldn't see blank, you would see pictures here.
Yes, that is correct.
So Zoom's recording overlays it because you can't see it even if I put it there. That's interesting to me. I'm glad you said something about that. I wonder if there's yeah, see, I'm guessing if I say hide video panel, it's going to hide it from me too. I don't know. I'll look into that. That is interesting that you say that. I mean, not being able to see what's on your side of the screen, I would have never guessed that it treats that video window separately. I would have thought wherever I move it, if it's on my screen, you would see it. You would see yourself. Like, can you see yourself right now on the screen? Like,
No,
right
we can't see ourselves.
You are right in the middle of the screen right now. My slides. Okay, that is interesting to me. I'm going to look into that. That's I'll see if I can get that fixed in the future. All right. Okay, so let's talk. Oh, so first of all, before I go on, are there any questions about the homework? At least questions right now. Others can come up during the lecture if you want, because I'm going to start talking about kind of the same stuff from a different angle. But does anybody want to ask some starter questions before I dive into file systems? All right. So let's talk about memory. And I think this is where we start connecting back. So we have different kinds of memory, right? So we have hardware registers. So I'm going to do this kind of in the from fastest to slowest, let's say. So we have hardware registers. We have L1 cache, L2 cache, okay, L3 cache. Then we have system memory. This is our computer's RAM. Then we have our hard drive. So HH or HDD or SSD, depending on the technology that's being used. But then if you want to keep going, you have like your CD/DVD slash floppy, whatever. We're going much older school now. Very rarely are we'll even put floppy on its own line. Some of you may still have computers that have a CD or a DVD drive in them. If you buy a new computer today, very rarely do they have those unless it's like a server. Some servers still have DVD drives because some of the installation media, so they can keep it proprietary, comes on DVDs still instead of digital downloads, or at least that's as an option, so people can't digitally steal the stuff, whatever. Floppies, many of you have never actually touched a floppy disk? Has anybody in here never, like you've seen them in movies or something, but you've never actually physically held one? Has everybody held a floppy disk at some point? So this is our 5 1/4 or 3 1/2.
Don't forget the 8-inch.
Well, there's even bigger. If you keep going back, the discs get bigger and bigger and bigger. There's floppies that are, I don't know, they're probably I'm guessing it's like a 12 by 12. That used to be like, you know, server farms. And I think it probably held probably 32K of memory, 32 kilobytes of memory on a 12-inch by 12-inch floppy disk. So we're not going to talk about this at this level. We're going to see these are really, really slow. These are very slow. So we're going to just do this in terms of speed. So if this has a speed of a 10, now you would have quite a bit of drop off here, but we're just going to go in order. So this would be a 9, this would be an 8, 7, 6, 5, 4, and then, you know, you have your 3, 2, 1, and then the last one is a rock. That's a speed of 0. Right? So the idea is that now one thing we would see actually here is this is our CPU. So all this stuff is faster the closer we get to the CPU. I actually have these in order of commute time. Let's say if you looked at your motherboard as like an interstate system for driving, the commute time from a hardware register to the CPU is very short. You basically live next door. Whereas if you're going from the hard drive, because really this is where we're going to be talking about today. This guy is, you know, a pretty decent commute. You know, it's going to be a long drive, relatively speaking. All right, and we can really think about memory in this fashion because there's really two sides to this, right? Two ways to measure memory. We have the technology itself. So this is read, write, speed. You know, and then we have the interface to the memory. So this is like the highway that data travels on to move between the source and the memory. And let me actually give you kind of a real life example for this. And actually, it's a very recent example as I went and did a recent network update. And actually, this just popped in my head. It wasn't a plan I was going to do, but hopefully this, again, reinforces this idea. We're talking about the same thing. We're talking about bits traveling between point A and point B, where point A and point B are things that know how to deal with bits, whether it's storing bits or transmitting bits to something else. Everything we're talking about right now is ways of representing data. And we're representing it on a medium, and we get to choose how we're going to represent it. And however we represent it is the way that we're going to be forced to deal with it. So here's the example here that would be a problem. So I'll show you a picture of what went down recently at my house. I would probably hide children's eyes and what went down recently at my house. All right, so in my house, I have a router. So this is how my internet is hooked up. So I have my cable modem coming into my house. My cable modem feeds into my router. My router gives off Wi-Fi, and my router also runs a wired network throughout the house. So that wired network has 3 nodes coming off it. I have basement, or you know, this is the old awesome fat offices. Main floor, upstairs. All right, so there is a physical wire going from this router to this wired network that travels to 3 different levels of the house. Okay, so, and each one of these guys has a switch. So at this point, we're talking about network hardware, so I'm not going to go into that. It's unrelated to what we're talking about here. Okay, so we have a switch there. We'll say a router is also green. That's network hardware. These guys are, let's say, ideas. All right, and this is my internet source. That's where my internet comes from. All right, so now one thing I noticed is now usually if you're doing, so you on your Wi-Fi, you have your laptops or your cell phones, things like that. If you do a speed test on Wi-Fi versus a speed test on the wired network, it's pretty common that your Wi-Fi network will have a slower speed test. Just the nature of Wi-Fi and the distance you are away from it, and how radio signals degrade, things like that. But the speed you're going to get over that Wi-Fi network is going to be probably fine. But you won't, the best way to test your maximum speed of your internet is not to test it over Wi-Fi. You want to test it directly as close to the cable modem as you can. All right. Now, my house has gigabit internet. So this guy is 1 gigabit per second down by 35 megabit per second up. All right, so this is the download speed is substantially faster than the upload speed because they don't want me running servers out of my house. That's normal consumer internet. That's how it works. All right, so this is pretty fast download speed. So gigabit internet is 128 megabyte internet. So 1 gigabit is the same thing as saying this is 1,024 megabit. Internet. So some of you measure your internet speeds in megabits. So, normal spectrum internet is 200 megabits, let's say. The ultra fast spectrum is 400 megabits, and then they have their gigabit super fast one. So I have 1,024 megabit per second internet, which comes out to 128 megabytes per second maximum throughput. Now, when I was doing the transition to having to do everything over Zoom, my office is down here in the basement. I did a speed test from my laptop plugged into, even though around the house is on the wireless network, down here it's on the wired network. All right, so I have a wire coming from my router over to my computer and plugged in through an Ethernet cable to my laptop. And I was getting speed tests in the range of about 100 megabits per second. Now,
is this a subtle way to flex on us?
Oh no, 100 megabits per second is garbage.
Maybe for you.
I get
I'm
it.
out here with like 4.
I think we all knew when we started, if you follow, I mean, keep in mind, I've said this to you guys for a long time, you should know what your internet speeds are. You already knew I probably had faster internet than you right from that one, okay? Some of you don't know what gigabit is, but it's a number that you don't see on the commercials. So it's probably, it's probably something that you're not.
Yeah, a little bit.
All right, but In any case, I'm supposed to be getting 1,024 megabits per second, you know, or in that ballpark. I was pulling 100 megabits per second. That's 10% of the speed I was supposed to be getting. So then the question is what's the problem? All right, so now I'm going to connect this to what we are talking about here, so it's not just a Littman internet question. So we have some options, right? On one hand, I have my laptop. All right, so my laptop here has an Ethernet port. So my laptop is connected. Really wish that would stop dropping down. My laptop is connected to this switch over Ethernet. So that's a physical cable connecting my laptop to this switch. And in fact, it actually is a green cable. I'm looking at it right now. All right, so there's a green cable connecting my laptop to this switch. So my laptop is physically connected to this. So the first question I might ask is, can my laptop accept faster than 100 megabits per second? All right, so my laptop has a gigabit network connection, so it should be able to accept up to 1,024 megabits per second. So the question is my laptop the bottleneck? Is the question I'm asking. Am I sending data? Is the data coming across this pipe at 1,000 megabits per second, 1,024 megabits per second, but I'm actually only able to receive it at 100 megabits per second? That is, the interface to that data is my slowdown. Am I able, if this is traveling, I should have data traveling along this wire here at 1,024 megabits per second. Coming to my laptop, we think about my laptop is the thing that's using that data that's coming in there. So I have this interface that goes from this Ethernet cable that's coming from my switch over to my laptop. The question is that the guy that's bottlenecking the 1,024 megabits and only allowing me to realize 100 megabits per second on my computer? That's one possibility. All right, so tested that, did a little separate local area network type test. It was fine. That was going through this switch. So I can send data to another computer hooked into the same switch, and we can move data up to 1,024 megabits per second, no problem. So my laptop can handle 1,024 megabits per second. My switch could handle 1,024 megabits per second. So then the question is, well, is there something wrong with my cable modem? So to test this, actually, I don't even need to do that. I connected my laptop directly to my cable modem. And I started getting 1,024 megabits per second. So if the communication between my cable modem and my laptop is good, the communication between my switch and my laptop is good, the problem here must be this guy right here. So what had happened is something on the board in my router. So a lot of times when you buy a router, they're listed as, the text you'll see on it is something, it'll be like 10/100/1000. These are all megabits. So 10 megabit, 100 megabit, 1,000 megabit, or you can think of that as gigabit. Router, switch, whatever. It's capable of those three modes. You know, and now if you're running larger networks, there's 10 gigabit, and even more than that. But like Concordia has a couple of 10 gigabit pipes, but I don't think most consumers are going to have a 10 gigabyte pipe in their house yet, because we don't. I mean, at some point I'm going to need more. So for instance, if next year they come out with the 2 gigabit per second internet, let's say that's the case, and I upgrade to that, well, now all of a sudden I have faster internet than any of the equipment in my house can handle. My laptop can't accept it faster than a gigabit per second. My switch is only a gigabit switch, so it can't switch data faster than a gigabit per second. So everything in my house would need to get upgraded as well to actually take advantage of the full speed of that. Now, the reality is, and this goes back to what Luke was asking, is this a flex thing? I mean, am I ever really using 1,024 megabits per second on this laptop? Every now and then, if I'm downloading something over a torrent or something like that, where I'm pulling from a bunch of different sources, maybe I can maximize my internet. If I'm doing something that really specifically is attempting to do that, right? I'm downloading a 75 gigabyte file, and I'm pulling from 50 different sources that are each able to give me it at some sort of maximum speed, and all those add up to 1,024 megabits. Maybe I can maximize my internet connection. But that's not why you get an internet connection like this, because realistically, when you download a large file, you start downloading it and you walk away, right? You get the download started, you go to sleep. Do I care whether it takes 15 minutes? Well, here, let's put it in more real time. Do I care whether a download takes 3 hours or 8 hours? Either one of those, I'm not going to sit around and wait on it, right? I'm going to start it, I'm going to go to bed. So I don't really care if it takes 8 hours to finish downloading or it takes 3 hours to finish downloading. So I don't need fast internet like this for a single source. Instead, when you get faster internet, what you're really talking about is kind of like water flowing into your house, right? So you have a water line that comes to your house, and if you have one person taking a shower, their water pressure might be fine. If 2 people are taking a shower at the same time, you might notice that there is a little drop off in water pressure, because now the bandwidth coming into your house is a little bit less, right? Now, if you get 3 or 4 or 5 or 10 people taking showers all at the same time, if you have that many bathrooms, I guess, unless you have a substantial bandwidth coming to the house, you might notice that you have a drastic drop in water pressure, because now your water is getting divided up to among too many people using it at once, and there isn't enough source water coming through to give that to you. That makes sense? So when you get faster internet, it's not any faster for an individual application. You know, if you have 5 megabit per second internet or 1,024 megabit per second internet, both of those are sufficient for watching or for using like Zoom, for example. You know, video streaming and things like that. You want to do like 4K streaming, they recommend like 30 megabits per second. So let's say you had a 50 megabit per second internet. So 50 megabits per second versus 1,000 megabits per second are the same speed. Your internet quality won't be any better or worse for download, for streaming. The difference is that after I'm streaming one 4K movie, I can go and stream 40 other 4K movies. Where if you're on a 30 megabit per second internet connection, you can only do one at a time. All right, so does that start making some sense? What the difference between internet speeds is? It's just a total amount of, think of it as water pressure coming to your house. All right, so this isn't anything crazy scientific-y or whatever. But in any case, when I was talking about this router thing, this thing has 3 different modes it can operate at: 10, 100, or 1,000. 1,000 would be gigabit. At some point in time, I don't know if it was a power surge or heat or whatever, the mode for 1,000, that circuitry was no longer working. So the router dropped down to 100. So even though I was feeding it with 1,000, and the thing is, I haven't done a speed test in forever. I have fast, crazy internet. And I was able to get at least 100 megabits per second at any individual source. So I didn't, and I just mentioned like Netflix recommends 30 megabits per second for 4K video, right? 4K video, that's the best you're gonna stream it at this point in time, right? So if you can stream 4K video, you can do anything at any individual source. Fair enough? So punchline is I never had a reason to check my speed. I was getting 100 megabits per second to every device in my house. I just was never getting any more than that to any individual device because my router here, which sits, I don't know, call it 6 inches from my cable modem, was taking this 1024 and only feeding it to all the networks at 100 megabits per second. So I've only been using 10% of my internet for who knows how long. So in any case, I replaced this router and now I'm getting the 1000 again here. So I get, 1000 megabit per second connection here and all that jazz. So what does this relate to? How does this relate to memory? What's moving along these lines is bits. A lot of times we measure them in bytes, right? So, bits versus bytes. I want to ask a question here. Why choose one over the other? Why is my internet advertised as 1 gigabit per second internet instead of 1024 megabit per second internet instead of 128 megabyte per second internet? What do you think?
Gigabit sounds more impressive than 128 megabytes.
Okay, that's probably true. So right now, this whole gigabit per second, this is like a weird word to people, right? Especially if some of the advertisement is put 1 gig internet, something like that. But gigabit per second, this is kind of a newish thing. So people just look at this and say, oh, this is the next thing. It must be super fast, whatever. Okay, so we'll call this guy an outlier. So then if we'll apply the same answer. If I'm just asking between these two, why would they call it 1024 megabit versus 128 megabyte? As computer scientists, we know that this little b means this is measured in bits. We know that this big B means this is measured in bytes, a multiplier of 8, right? All right, so the message there, I think it was Eric that said that, right, is that 1024 looks like a bigger number than 128, right? Because to the layman, and I have found too often to the computer science student, this and this are the same, even though we know it's not, right? This is a measurement in bytes. This is a measurement in bits. 1 byte is equal to 8 bits. All right, just like recently for the homework, we've been talking about 4 bytes being equal to 32 bits for the size of our memory addresses. Okay, so these are all the same ways of talking about the same stuff. If we're talking to consumers, consumers like big numbers, right? So, at some point, you saw this for a long time, we could take this even further, right? We can say, well, this is actually, let's copy this number. That's 1 million kilobit per second internet. Or that's 1 billion bit per second internet. At some point, the numbers start becoming ridiculous where these no longer seem sexy anymore. And people who've been around since the dial-up modem age remember this K thing. So they don't necessarily perceive something that starts with a K as being extra fast. So even though this is a giant number, they might get suspicious. So this is the consumer sales model. But up here, the M, the M stands for mega. That's gotta be good, right? It's gotta be good, gotta be fast. So they would rather put the M on this guy. And the idea is that the little b versus the big B to a consumer is meaningless. Even though as computer scientists, we know that the big B is a measurement of bytes and the little b is a measurement of bits. So the big B counts for 8 of the little b's. Does that make sense? All right, so that's why our internet is usually advertised in megabits. And now we're just starting to transition towards this gigabit stuff where, you know, people have been used to gigabit and or gigabyte hard drives, 300 gigabytes, 700 gigabytes, terabytes, 2 terabytes, 3 terabytes, that type of stuff. Go ahead, Josh.
Isn't another reason kind of more historical in how we represent speeds in serial versus parallel communications? Because networks are mostly serial, aren't they?
Well, actually, networks are mostly serial.
In terms of the internet.
That is so related to the question. I don't know if you realize it, but that's so related to the question you've been asking about your memory. So, who dictates what a network does? I guess that's what I'm going to get at. So, serial versus parallel. Let's just throw it in here, just so we. So serial, like Lucky Charms, Fruit Loops, serial sends data one. Well, here, this is I'll connect it right to your thing. Sends data 1 unit at a time. Parallel sends data many units at a time. And we typically 8 is what we think about as parallel for the number of units, but it'll be some power of 2 units at once if we're dealing with it at the level of on a computer. All right. Now, when I say unit here, when something is sent over a serial connection and we're sending it 1 unit at a time, because you mentioned that, oh, well, typically networks send things serially versus parallelly, right? What's a unit? What is that guy? What are my options for my units? Well, my units can be bits, they can be bytes, they can be kilobits, they could be megabits, they could be megabytes, they could be kilobytes, so on and so forth, right? I'm measuring those guys differently. So I'm sending 1 unit at a time. Now, 8 bits is the same thing as saying 1 byte. Those are different ways of saying the identical value. Just like you can give the same temperature outside in centigrade, centigrade, Celsius are interchangeable, but centigrade, Fahrenheit, and Kelvin. Actually, you know what, Appel, I can see you living in a world where all temperature is given in Kelvin. I don't know why that's true, but that sounds right.
That sounds right.
That does sound right. But in any case, when we give a temperature, right, today, I don't know what the temperature is outside, I haven't been out yet, but I'm guessing it's mid-30s or something. It's somewhere in that cold streak. So 30 degrees Fahrenheit, somebody from Europe wouldn't really know what that means. If I said it's 30 degrees outside, they basically would think the Earth's on fire, right? Because that's really, that's very hot in centigrade. So the idea is that, these are different ways of expressing the same value. Make sense? The values are the same. We're just giving them in different units. Same thing's true when we are dealing with computer data transmissions, is we give things in different units. So when I send stuff over Ethernet cable, over a network, I'm sending it at a speed. That's, we're thinking about a network as kind of like a map. with a whole bunch of interconnected highways, right? And when you start thinking about your map, if I'm driving from here to Milwaukee, I'm probably going to get on 43 because 43 has a 70-mile-per-hour speed limit. So assuming we don't we don't exceed the speed limit, I know I can go 70 miles per hour. Now I can also convert that into kilometers per mile. If I really wanted to, I can also give it to you in millimeters per second, right? Or I can, so there's all sorts of different ways I could express that same value, even though it ultimately is about a speed. We're thinking about how fast can my car get from Mequon to Milwaukee at maximum speed allowed across that network connection on I-43. You know, if I take more residential roads that have slower connections, I have to maybe go through, different intersections where I'm slowed down. That's like a switch or a router or something like that, where I have to go through some sort of process before I'm allowed to switch to the next street or go over to something else. This is how computer networks work, right? It's modeled after real life, just like everything else that we do with programming and stuff. It's all modeled after how we already solve problems in real life. So we have these pieces of computer equipment that model that for us, all right? And sometimes our goal is to get from point A to point B as fast as possible, but sometimes speed isn't all that important. Sometimes accuracy is the most important, and any speed that's fast enough is good enough, okay? You measure everything in joules, kinetic energy. Like the super geeks who I saw something the other day, because there are people who have learned to speak fluent Klingon, old Trekkie fans and some of that. And there's some group that has decided now, or at the end of the world, they just converted to Klingon. They will only communicate in Klingon. They have their own little group of people who Google this. So they've started their own Klingon village online where they only talk in Klingon. It's a thing. All right, so, in any case, that's how computer networks work. How we send data, so for instance, serial would mean we have a one-lane interstate where only one car can travel at, well, we can have multiple cars traveling along the interstate at once, but only one car is at the same point on the interstate at any point in time. You would never have a car next to you because there's only one lane, right? But in parallel, you would have 8 lanes of traffic where you could have 8 cars right next to each other, all traveling in parallel at the same time. That's serial versus parallel. That makes sense? So if I have 50 cars that I need to get from point A to point B in the fastest way possible, and I can travel at the same speed, whether it's in serial or it's in parallel, I can get 50 cars to the endpoint over parallel, over 8 lanes of traffic more quickly than I can get 50 cars to the endpoint over 1 lane of traffic. Okay? This is taking out of consideration any sort of slowdowns that you might have, the overhead of managing multiple lanes of traffic and stuff like that. But, so on its surface, parallel seems like it's better than serial. Okay? But now you have an issue of what happens at the very end. Well, at the very end, when we're all trying to get to the destinations, we're all trying to get to McDonald's. All right, so we have 8 lanes of traffic. We're all going at maximum speed at 8 lanes of traffic. And since nobody's going to break the speed limit, we're literally right next to each other, all going 70 miles an hour. And we're coming up on McDonald's. And now McDonald's has a single entry, a single interface. This guy right here, okay? A single interface to get into their parking lot. And not that our interstates connect directly to McDonald's, but in some cases pretty close, especially if you go through Chicago. The Oasis is having almost every one of them is a McDonald's, and the interstate is directly connected to it. All right, so those 8 lanes of traffic ultimately have to take that single lane exit. And that's a point of congestion, isn't it? Whenever you have traffic backups on the interstate, sometimes that backup is because there's people are coming on and off the interstate on that one exit, and it's causing everybody else to have to slow down. That makes sense? All right. So even though that 8-lane interstate for most of the time traveling was perfectly fast, we didn't have any problems, whatever, as soon as we had to transition to the next connection, things slowed down because now we had to have some sort of communication of who gets to go first and things like that. Well, in computers, we can decide to have oversight where we have people flagging them through, or we can just hope for the best and let everybody just try to take the exit at the same time. And anybody who crashes and data gets destroyed, you just resend the data. That's what TCP/IP is. TCP/IP is saying, it governs crashes. So it says, hey, if I'm going to send a bunch of data over this network, I'm guaranteeing that data will arrive eventually. So let me know. We're going to have a communication protocol. So we use Internet Protocol. IP is how we're talking over the network. You let me know if something doesn't arrive on time, and I'll resend it because I have a duplicate of it. I've maintained a copy, and I'll resend it until everything finally arrives. Whereas we don't have that ability in real life, correct? In real life, if we're all driving to that McDonald's, even though we were all going the exact speed limits, we're all getting there at the same time. When we had to go from 8 lanes down to 1 lane, as human beings, we decided we had to self-govern ourselves to make sure that we all survived the entrance into the drive-through. Does that make sense? Because we don't get a do-over. All right, we all just exit at the same time. That's a version of networking. Okay. So when we think about going from one place to another place, we can sustain a certain speed, a data rate, but those transitions are points of failure. When I transition from my router to my wired network over these switches, this was a point of failure. This was a point of failure. This was the originating thing. And then before that is something that's out of my control, right? I could have a bad cable modem. I'm looking at my cable modem right now. If that goes bad, I can have my cable modem replaced. But if everything inside my house is working, then the problem is something before that. It could be a cut fiber wire that's in the neighborhood because they were doing some construction or something. It could be a problem over at Spectrum with some of their network connection where they're not delivering it to my house, whatever it is. So I can only control what I have, direct access to. But the point is that if we go back to where I started here, this idea of memory, we have our CPU that's inside of our computer. We have things that are, all these things, a hardware register, L1 cache, L2 cache, L3 cache. These things are all built for holding units of stuff. And we get to decide what those units are, and we get to decide how big these things are. So typically, hardware registers might hold 16, 32, or in modern cases, 64. Let's just say 16 or 32 for us. 16 or 32 bits, which can also be written as 2 or 4 bytes of data. That make sense? All right. So now L1 cache, and almost all of these have to do with efficiency. So these first 4 here, this guy is the fastest we're going to get. This is sitting right at the mouth of the CPU. All right. So if you're eating lunch, if you're the CPU and you're eating lunch, this guy's right in front of you. You can feed off registers all day long, and you're going to get that into your mouth as fast as possible. L1 cache, cache memory is often larger than your hardware registers. They're still very fast because they're pretty close to the CPU. But the job is when we think about, well, here, let's just put something in here. I'm going to say L1 cache. I'm going to say this is 128. Let's say maybe kilobits. 128 KB. All right, and that is 128 times 1024. That's 131,072 bits. 131,000. 1,072 bits. 131.72 divided by 8, or 16,384 bytes. 384 bytes. All right, so I'm calling this the fastest. I'm calling this the second fastest memory. Do you notice the capacity difference? A hardware register can only hold 16 or 32 bits. That is the same as saying it can hold 2 or 4 bytes. The next level out can hold 131,000 bits, or 16,000 bytes. And I'm just making up numbers for this guy, but this is pretty close. 128 kilobit L1 cache is possible. Maybe it's 64K, maybe it's 32K, but it's in the Ks. All right, it's going to be something kill something. All right. Similarly, we get out to L2 cache, and sometimes you see this in the difference between like server processors, like Xeon processors, and normal Pentium processors. Sometimes you'll see you can compare a Core i7 processor. Maybe this guy has 1 megabyte of L2 cache versus maybe 4 megabytes or 8 megabytes of L2 cache on a Xeon processor. So we'll just call this a server chip. So we're going to call this guy, he's going to have a 4 megabyte L2 cache. Big B. Big B. So that is 4 times 8, so that's megabits, times 1,024 is kilobits, times 1,024 is bits. So this guy can hold this many bits, or divided by 8. This many bytes. Okay, so now we're trying to talk about these guys in the same units to give us a, so 2 bytes versus 16,000 bytes versus 194,000 bytes. We get to L3 cache. Anybody know the difference between L1 and L2 versus L3?
L3 is shared between cores, isn't it?
That's the big thing. So this is shared memory between cores of a CPU. So this is measured a little differently because most of our CPUs no longer are single core CPUs, right? You have a dual core or a quad core or a 6-core or an 8-core, an octa-core processor. So each of those cores has its own collection of hardware registers, its own L1 cache, its own L2 cache. But then if you need stuff to be load balanced across CPUs, the operating system that's supporting multiple cores, it can use L3 cache for communication between cores of a CPU. All right, so I'm going to skip over L3 cache here for our numbers. It's kind of a special purpose thing, but you know, you would have 2 megabytes, 4 megabytes, 8 megabytes, you know, stuff like that, depending on the nature of the architecture you were working with. All right, but relatively unimportant. Why is this modified by me at 306? Go with that one. I drop off the internet or something as I'm diagramming my network problems. All right, so hardware registers are right next to the CPU. L1 cache is a little bit farther away. L2 cache is a little bit farther away, but these are still on the chip that we call the CPU. Right? If you held up an Intel processor, you would say this is the CPU, but inside of that guy will be your registers, L1, L2, and L3 cache, all inside of that single chip. Because the actual processor is only a part of what we're looking at in that hardware processor, that chip. All right, so registers L1, L2, and L3 cache live on that single chip. Now we have our system memory. So again, if we're drawing a picture of our computer, because remind me, what's an operating system? This thing we're working on right now, what's its job?
We call it a program that runs other programs.
Okay, give me something. Let's start with this. What's a computer? A computer is a collection of components, right? So we have a CPU, and we talk about our CPU. What we have here is we have register, L1 cache, L2 cache, L3 cache. We have system memory. This is our RAM. That's another component of our computer. We have our hard drive. So HDD or SSD. That's another component of our computer. Okay, let's just leave it at this because you might also have, here, we'll put your DVD drive. Even though those are becoming less and less common now. So these guys are all components of our computer, right? Now, how are all these components connected with each other? We have the motherboard. All right, so when you go and get your, buy your computer, you're building your own computer and you buy a motherboard, you get this big board that has a whole bunch of crap on it. And it's got a little socket somewhere you can drop your CPU in. It's got some interfaces where you can click your system memory in, and it's got some ports, serial ATA or whatever that you can use for connecting your hard drive and your DVD drive, right? So you have ways of interfacing your system memory with this motherboard, your hard drive with this motherboard, DVD with this motherboard, your CPU with this motherboard, okay? And this motherboard has on it ways for the various components to talk to each other. All right, so the CPU itself, it has its own little kind of close-knit group. So inside of the CPU, we have our own little neighborhood where these guys have communication channels for talking to each other. But it all happens locally, so you don't have to leave your gated community for the CPU to talk to registers L1, L2, or L3. But you want to start talking to system memory. You want to talk, so in our so in box, we had this guy is 32 megabytes, right? You know, and that's the same thing as saying 32 times 1024. That's bytes times, or that's kilobytes times 1024 is bytes divided by 8 is bits. So that's a 4,194,304 bit of memory. All right, is what 32 megabytes is. All right, so that's the system RAM that we have. Now, we decided that system memory has a speed of 6. So I'll go ahead and let me put this chart here. Actually, I'm going to write it like this. And we said that a hard drive has a speed of 5. Now, the drop off is actually bigger than that, but we can at least represent it as being slower. And the DVD thing here has a speed of 4. And then within here, I'll go ahead and I'm going to just draw this differently. There's L1, L2, L3. So a little bit farther away, a little bit farther away, a little bit farther away. Oh. So this guy has a speed of 1. This guy here has a speed of 2. This guy here has a speed of 3. This guy here has a speed of 4. Okay, so if we think of this as like a map of the Milwaukee area, okay, and this is the place to be, the CPU. This is where everybody wants to be. Okay, we see we have all of these. So this is a really expensive neighborhood, right? Okay, so right here, right next to the CPU, we have these registers. This is like oceanfront property that, you know, your mansions, although it kind of works backwards. This is oceanfront property, tiny homes. This is a little bit farther away, but a little bit bigger homes. This is a little bit farther away and even bigger homes. This is a little bit farther away and even bigger homes. But all of these homes are pretty tiny compared to these giant mansions out in the boonies. All right, over here. So if I live in one of these tiny homes here and I want to get to the CPU, I only have to go to like the end of my driveway. I can zip down there real quick. So I can travel at a speed of, well, actually, I did it backwards, didn't I? So this is a speed of 10, 9, 8, 7, 6, 5, let's see, 7, 6, 5, and 4. So I can travel at a speed of 10 and get over to the CPU really fast. If I'm at L1, I can get to the CPU at a speed of 9. A little bit slower, a little bit slower, a little bit slower, a little bit slower. But actually the drop off from L3 to system memory is a pretty big drop off. You know, if this is a 7, this guy is probably more like a, I don't know, a 3. And if this is a 3, this guy is more like a 0.1. So the speed of a hard drive is way slower than the speed that we can communicate with. Well, actually, I got to think about it a couple different ways. These communication channels are called buses. And these guys might all have similar speed, the buses themselves. So these numbers I'm representing have more to do with the actual hardware, the devices. So the register, the L1, the L2, L3, the system memory, the hard drive. So I'm really talking about the interfaces that slow down. A little bit ago, we talked about if you're driving a car on the interstate and you want to take that exit to McDonald's, that exit is a point of slowdown. That's the interface between the interstate and the stopping area, the McDonald's Oasis thing, okay? So this is the speed at which we can communicate with these different things, one way or another, okay? And it's because the interfacing for memory is slower than, for your system memory, is slower than the interface for L3, which is slower than the interface for L2, which is slower than the interface for L1, which is slower than the interface for registers. And then your hard drives are even slower. All right, that makes some sense? But any way you cut it, we still have bits flying across these communication channels. Okay, when you're looking at a map of the world, doesn't matter what the road looks like, whether it's an interstate, a back road, a gravel road, whatever, it's still cars that travel along those roads. And they move from point A to point B on those roads at some speed. All right. So this is what our computer looks like. The job of the operating system. Oh. Let's get this guy here. The OS. Put that in green here. So let's just put it in the text box. Manages the communication between these components. And when what we mean by manages, let's start off with this. Does a computer need an operating system? Is a computer still a computer even if it's not an operating system? Or even if it doesn't have an operating system? What do you think? Is an operating system required for something to be considered a computer? It's not rhetorical. Give me your take. You paying attention, V?
Yes.
What do you think?
I think what?
Do you think that a computer can still be a computer even if it doesn't have an operating system? Are operating systems required for a computer to work? That's the question.
Well, without anything running it, it's just a piece of plastic and fancy machinery.
Okay, what do you mean without anything running it? What do you mean by that?
Without any software telling it what to do, it's basically useless.
Is it?
Most cases.
Well, I mean, you couldn't use like a keyboard or anything. You just like plug it in. Like, how else would you use any inputs? Like, how would you input information?
Okay, so you're wondering.
Oh.
So you're saying that, well, maybe a computer has some function without an operating system, but we still need to have some way of interfacing with it. A human being needs to have some way of telling the computer what we want it to do.
Right.
So, like, for instance, is a car still a car even if it has no steering wheel? Sure.
Yes.
It's just going to be more difficult to drive, right?
More fun.
Possibly more fun. I actually had this conversation with somebody yesterday. When we talk about fuel efficiency and things like that, how come we haven't, I don't want to get too far off the topic on this, but it is related. I mean, so it's just a loose relationship, but when you're on the interstate and let's say you're taking a big long road trip and you're going to be on this interstate for 7 hours, how come we don't try to hit our speed and then put the sails up? Why can't we put a sail up on your car to let the wind partially power our car, catch the direction of the wind so that we can, travel without fuel or less fuel? How come we
Because
don't?
we're not sailors, duh.
Why not? I mean, before we had cars, everybody was, we had the horse and buggy and things like that, but boats have been around for a long time. But what if you can get, 700 miles per gallon on road trips if you just use the engine to get you up to speed and then turned it over to sails? Just had the wind take you.
I don't know, man. Friction's pain in the ass without water.
It's the oil companies. They don't want you to know.
It's
Oh yeah, true.
the oil company. All right, but so in any case, using our car as an example, a car without a steering wheel is still a car. We just need to come up with other ways of getting that thing to turn, right? We can maybe lean into it, something like that. So we could come up with alternative ways of controlling a car. So if we're thinking about an operating system in terms of a car, we're thinking about our input devices, as Fran pointed out, was how to use the mouse, how to use a keyboard, how to use these things that we have this preconceived notion are ways of inputting into our computer, even though there's zillions of different ways of input into our computer, isn't there? If you go and get one of those Arduino kits, they come out with, I'm having my graduate embedded systems class go through and go through these projects with Arduino circuit boards, and they're using all sorts of different sensors. They're heat sensors, they're sound sensors, they're moisture sensors. There's all sorts of different ways of getting input from outside of the computer, bringing it into the computer and doing something with that input. Okay, and sure, as you pointed out, Luke, software makes life a lot easier because software is quick to change, right? We can make a quick little update to software real fast and we're good to go. Whereas if we built something in hardware and we found a bug in it, oh, they gotta go and get a soldering iron out, start melting some stuff and patching up your bug, right? Now, we can say that maybe that's faster if it's just metal to metal all the way through, because now you're not having to go through that slower software portion, but the software is more easily changeable. All right, so we're playing this balancing game between what allows a human being to be creative with the equipment versus what gives us the speed that we demand, right? So most of our computers are hardware based in that somebody somewhere spent a lot of time, a lot of money, a lot of whatever to create these hardware systems that were really fast. Okay, but they had bugs in them. They just had to test them until they got all the bugs out, or at least the majority of the bugs out, because they were going to ultimately effectively write this in ink, right? So like if you were writing a paper by hand, you want to write it in pencil instead of ink, because if you need to make a change, ink you have to scribble out. I remember when I was younger, they had erasers for pens, but if I recall, they never worked. So I'm not sure that's really a thing. But pens don't erase as well as pencils, but none of them erase as well as the backspace key on a keyboard. So those work much better. But the punchline is that the more permanent something is, the more careful we have to be to get it right the first time. Okay, and software gives us the ability to be very flexible in that we can go and change it. And we only really have to worry about major bugs when we actually release it into the wild, depending on how useful or how mission critical that code that we just released is. All right, so if a car without a steering wheel is still a car, a computer without an operating system is still a computer. It's just harder to interface with, right? We still need some way of telling that computer what we want it to do. That kind of stuff. Does that make sense? All right, so then what's the job of the operating system? What does the operating system do? The operating system The job of the OS. So we can say the steering wheel, gas pedals, transmission shift, whether it's manual or automatic, etc., are to a car as the OS is to a computer. That is to say, the OS, this gives us abstractions for more conveniently using the computer. And really, when I say us, I'm saying humans. Gives humans abstractions for more conveniently using the computer. So it gives us a way of translating. So we have these external tools like a keyboard and an external tool like a mouse. You know, what ultimately do we want a mouse to do? We want a mouse to allow us to point at things on a computer, on the computer screen. So when we move our hand on the mouse, that's translated into inputs into the computer that are then translated into this little moving arrow thing on the screen, right? That's what we expect it to do, and the operating system is going to provide that ability for us through one of its many abstractions. All right, so what are these abstractions? We have an abstraction for managing the CPU. We have an abstraction. Here, let's do it like this. For managing the memory. We have an abstraction for managing the file system, for managing external device drivers. So device drivers are like pieces of software that tell us how to make some external device talk to the computer. Now, some of these external devices are obvious, right? We assume that computers, if you go out and you buy a brand new computer today, you assume it will work with a keyboard. You assume it'll work with a mouse. You assume that it'll work with a printer. You know, you could probably add a little bit more to that list. But what if something that, what if next year we have a device that allows us to you know, plug something into our ear or something like that, and then we go into like real virtual reality. You know, we fall into some sort of digitally induced coma or something like that. Now we're into the virtual world, whatever. Well, that doesn't even exist yet. Could the computer you buy today possibly be compatible with that? Sure, through a software driver, right? Whoever releases that piece of equipment, they invent it. They also come with, you know, a download, a driver that tells your operating system how to how to communicate between that brand new device that comes out, you know, 1, 5, 10, 100 years from now, whatever it is, how to talk to the actual computer in the appropriate way. All right, so the job of this operating system, keep in mind the thing that we're writing here is not a requirement for computers. Operating systems do not have to exist for a computer to work. Operating systems are there to make us happy, to make the humans happy, all right? And the person who's writing the operating system, in this class that's us, we get to decide what's in the best interest of the humans we're designing this operating system for, okay? And this goes back to what we were talking about with our this homework assignment that's due next week. We decided that the best way for us to manage memory is to use 4-byte or 32-bit memory addresses to point to other places in memory. We just decided that. Okay? So one of the things that Appel has been asking me about is like, oh, well, when I'm using my Raspberry Pi, they always use 32-bit memory addresses. or a memory address looks like this, or a memory address looks like this. Who's in charge of those memory addresses? Let me ask you this. What's a compiler? This goes back to something from earlier in the semester. So a compiler converts high-level code into low-level code in terms of what two things? When I say low-level code, I'm talking about assembly code, stuff that runs directly on this guy, right? Low-level code runs on the CPU. It gets translated to machine language, but we'll say it runs on the CPU. So if the compiler's job is to convert high-level code into low-level code, it does this in terms of two different things. What are the two things that a compiler takes into consideration when it's compiling your C code into low-level code for into low-level code? We already
Where
have
it is in memory, maybe?
it again?
Where it is in memory?
No,
No.
I think we already have this slide somewhere. Okay, so the compiler, what's the advantage? So what's the advantage of high-level code versus low-level code? Tell me about that. Why do we like high-level code?
It's easier to understand when you're reading it if you know the language.
Yeah, human beings can write it. So we like high-level code. That's why we need a compiler. Okay? Our whole life is about being lazy, right? We want to have all these conveniences and we want to have all these conveniences so that the computer can work harder, right? So one thing is we want to be able to operate in a high-level language, a nice friendly language like C. Okay, I know that C is a little bit intimidating for us, but it's for good reason. I mean, hopefully you can look back now and see that, what are we, 12 weeks into the semester, 11 weeks into whatever it is. We're coming down the home stretch here, but think about your knowledge of C and a lot of some of this low-level binary and hexadecimal stuff. Think about what your knowledge of that is now compared to at the beginning of the semester, where just a simple C program was intimidating. So, I mean, even the worst of you, like Luke, or I guess Fran, we really come a long way, right? So we like C now. We probably don't like it as much as our Java or our C# or Python or whatever, because it feels a little bit less friendly. But wouldn't you say C feels more geeky? Isn't C in some ways like kind of more fun? Don't you feel more like a computer scientist writing C code than you do writing Java for Android or something? There's some truth to that, right? It feels more geeky. But when we write our code, when we use GCC, so when I'm talking about a compiler, when I use GCC, it needs to know what architecture I am targeting. And when I say architecture, what am I talking about architecture?
On the CPU.
Yeah, this whole thing. Okay, specifically the CPU, because this motherboard has all these things built together to talk to a specific kind of CPU. Not all motherboards are created equal, right? If the latest, greatest Core i9 processor came out tomorrow, it might not be compatible with the motherboards that are currently out there. It's possible they added something to it and it uses a different socket type or something like that. It might not be compatible with the current architecture. So you need to go get a new motherboard that has been updated to have all these communication channels, take advantage of the newfangled stuff and the newest Core i9 processor, whatever. All right, but I don't think it's unfair to say CPU. So it needs to know about architecture, where architecture is the CPU specification. Leave it a little bit generic, but I think that's fair enough. Okay, what else does GCC need to know about? It needs to know about the architecture. It also needs to know about one additional thing that we have purposely turned off in our GCC. Hopefully it's kind of connects some dots for us. Jack's saying what libraries it'll be included. Well, let's say that's close. Yeah. So what libraries are included means what do we already have available, right? So so Jack, you got no microphone today. So what are we doing in this class? What have we been writing? We've been writing an operating system, right? Now, operating systems, using Jack's lingo here, might be a collection of libraries, right? A collection of things that manage the communication between all these components. Now, since we're writing our own operating system here, we purposely told GCC to not consider any operating system when it compiles, because I'm going to be writing all the cool stuff. You know, don't target Linux or Windows or Mac. Don't target any existing operating system, because none of those libraries are available to us, because I'm writing my own. All right, but in the best case, the compiler targets a specific architecture and it targets a specific operating system. We have decided to keep, let's see, we've decided to deny GCC of the OS info, since we intend to write our own. So GCC doesn't get any of those built-in libraries, because those built-in libraries don't exist. We get the general logic of the C++ language. GCC is a compiler for the C language. It's actually compiler collection. So among the language collection, the language that GCC supports is the C language. All right, so so it knows how to do things like for loops and define variables and hold things like bytes and shorts and ints and longs and chars and blah, 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 blah. Those are the primitive components of the C programming language that have nothing to do with an operating system, that have nothing to do with an architecture. That make sense? All right, so now, keep going down this rabbit hole. Compiler output. What is the output of the compiler? I'm going to say after going through the linker. In fact, here. Remind me, what does the linker do?
It links various files that we have to like all run together for our OS.
Okay. So links the various low-level versions of our high-level code into a single what? You can say single document. Called an executable. All right, that's the thing we actually run. And that guy is going to run assembly language instructions on the CPU, and the CPU will call the correct magic tricks for what those assembly instructions say. All right, so compiler is going to say, I need to know what CPU specification we are using. So my question here is, let's go back to here. What is this for us? What CPU specification are we using? Who are we assuming this guy is? Yeah, i386. And who made that decision for us? Why is it i386? Somebody, well, Jack, you're cheating. So i386 is because that is what Box emulates. Right? We're using an emulator called Box, and Box pretends to be an i386 CPU. Does that make sense? And then we use that, if you remember, we have this this file here that allows us to tell it what's the BIOS that we want to have on our motherboard. Here's our CD-ROM stuff. Here's our amount of memory we have. So it's allowing us to describe for it the other crap that's on our motherboard. So it's emulating an i386 CPU and allowing us to say, okay, I have 32 megabytes of memory. And okay, I have this hard drive. We haven't defined one yet, and we may not actually define one, just so we can talk about it more at the high level. But we did define the DVD drive because we use that to boot our OS, right? When we compile, we ultimately are booting our operating system off of a fake CD-ROM. That's called our kernel ISO. All right. So Box allows us to describe the components that are part of our computer that are interfacing with this i386 processor that it's emulating for us. Make sense? All right. So for us, the architecture is i386 because that's what Box does for us. If we were not using Box, we were using something else, we had an actual physical computer, not something we were emulating, we'd be targeting whatever that architecture is. Okay, and the architecture just tells us what are the capabilities of this computer. You know, how many registers do I have? How big is L1 cache? How big is L2 cache? How big is L3 cache? L3 cache didn't exist with i386. L2 may not have either. But how big are all these? Actually, L1 might not have either. I don't think it did. Cache wasn't even a thing then, but whatever. So, you know, we're emulating this architecture, and then we are denying GCC of an OS. We're saying you can assume that there are exactly 0 system calls, 0 libraries available to you, because I'll be writing all of them. So we're saying GCC, you can't do any of your special magic trick stuff. You can't assume that some high-level code that I wrote already has some built-in mechanisms for like writing crap out to the screen, right? We invented that. We used our frame buffer. Okay, we used well, we didn't invent the idea of the frame buffer, but we used something that's built into the architecture itself. The i386 architecture supports frame buffer. It's part of it. That didn't come from software. That came from hardware. Okay, it says I will put stuff out to the VGA driver. You know, that's if we go back out over here. You know, we have our display library called SDL. So that's like our VGA card that's sitting inside of on our computer, the thing that hooks into the monitor. All right. and we want stuff to show up on the monitor. So we have to go through that guy, which is speaking the frame buffer language, right? Directly with the architecture for us to get stuff onto our screen. All right, makes some sense? All right, so we've had to tell GCC that we're targeting the i386 architecture because that's what Box gives us. And we've told it we are not targeting an OS. You can't use any built-in system calls that come with Linux, like how to write stuff out to the screen really nicely, or how to interface with a keyboard, or how to interface with a mouse, or how to interface with the VR thing that puts you into a coma, you know, whatever it is. We don't have any of those fancy things because we're going to write it ourselves on our operating system. This is what a compiler does. Compiler lets us write our stuff in C and ultimately convert it to an executable that will run on the architecture and the operating system that we're targeting. And since it's not running on an operating system, it is an operating system. This is a chicken or the egg thing, right? So we are writing the operating system, we're writing the foundation. So this guy's gonna actually write on the architecture itself and not take any operating system into initial consideration. It's gonna feed into the linker, which is gonna put all of those low-level code files that came out of the compiler for all of our different C files, and it's going to meld those guys all together into an executable that we can then run. Okay, and that's what our compiler output will be. Okay. So now we have our output, and this guy is supposed to run on the architecture. Now we have to think about our job as the OS is to manage the communication between these various components. Box has given us system memory. It's given us, well, it can give us a hard drive. It hasn't given us one yet. It gave us a CD-ROM drive. It gave us a CPU. It gave us a way of talking to these different guys through a channel. All right. Now I'm telling you that in real life, a system memory is much, much slower than registers or L1 or L2 or L3 cache, right? We're not dealing with L1, L2, L3 cache in our model here. We're just dealing with registers and system memory so far. Those are our world. So this is really fast memory versus much slower memory. And now we're about to think about much, much slower memory with our hard drives. But we've written all these components. We wrote a memory manager, a ghetto one, but we called it getmem. And it uses half of the system memory for keeping track of what's currently given, and the other half for what's for actually storing crap, right? So we've chosen to use system memory in that way. So let me go down here. What is the difference between register memory, system memory, and I'm going to call it hard drive memory just to be consistent here? What's the differences there? Hopefully this brings all the stuff together.
The speeds.
Speed. We already talked about speed. So, you know, the reason we use these different tools is relative to speed, right? And typically, register memory is fastest and smallest. Hard drive memory is slowest and largest. System memory is somewhere in between. Our registers are like 4 bytes. System memory is 32 megabytes. Hard drive space might be 400 megabytes. Or if we're talking about it in today's world with our modern processors, register memory might be 32. So let's say this is 4 or 8 bytes in today's world. System memory might be 16 gigabytes. Hard drive memory might be 1 terabyte. All right, so if we put this in bits, let's just keep it at 4 bytes. So that is 32 bits versus 16 times 1024 is megabytes times 1024 is kilobytes times 1024 is bytes. So this is 16 gigabytes, megabytes, kilobytes, bytes times 8 is bits. And then 1 terabyte is 1024 gigabytes times 1024 megabytes times 1024 kilobytes times 1024 bytes times 8. All right, so from a size perspective, do we see the difference? Relatively speaking, our registers today in our computers are still 4 bytes in size. We also have 64-bit registers. They do exist in our modern architectures. In fact, some server stuff even has 128-bit registers, but you know, we're not talking about massive sizes. It's tiny. But we make our jump to system memory, we're dealing with 137 billion bits compared to 32 bits. We go to our hard drive. Can I even read this number? So that's million, that's billion. So 8,796,000,000,000 bits make up a 1 terabyte hard drive. Really big, but very slow in comparison. So the things that we would store here are things that that take up big footprints, but don't need to be transmitted that quickly. Does that make sense? System memory sits in between. We put things here that need bigger footprints. See how much bigger modern day system RAM is compared to registers? Still a lot bigger, but it's, I mean, we're starting to get with hard drives, we're getting to the point where we can't read the number without thinking about it, right? And we're basically there with system memory as well. All right. So punchline here is that if you wanted to have an awesome experience, I mean, right now, when we deal with our hard drive technology, and this is just the capacity. This isn't even the technology. The technology of our registers, we don't really think about those anymore because they're basically soldered onto the motherboard or soldered onto the CPU. But like with our system memory, you know, we have different types of memory. So we have DDR4 or DDR4, DDR3. We have some different megahertz, you know, speeds within those. So there is an architecture to the RAM that says how fast is this memory compared to another type of memory. So there's two sides. When we think about memory, we think about capacity and we think about speed. So we consider, let's see, interface speed and capacity when we consider what kind of memory we're going to deal with in at a certain point in time. All right, so I've given you three different options here: registers, system memory, and hard drives. All right, so I'm naming these guys all memory. What's really the difference between them if we abstract it and just think about these guys as buckets. When we code for memory, what is the difference between these different types?
I have a quick question.
Yep.
How many registers do we have?
I386, I mean, the architecture tells us that. What is I386? I think we have 4 general purpose registers, AX, BX, CX, DX. And then there's a stack register. I don't know, something like 7 or 8 registers in I386. It's in the Intel specification for that processor. A Core i9 processor, a brand new, super awesome one, would have more and bigger ones. So again, that's part of, we didn't invent that. We're targeting the i386 processor, and that guy is what it is. That's like asking the question of how many cup holders does a 1997 Chevy Cavalier have in it? It has however many cup holders came with the 1997 Chevy Cavalier. This guy comes with the number of registers that all i386 processors came with, whatever that is. It's in the specification somewhere. And that's what Box mimics. Box pretends to be that. All right, so when we code for memory, what is the difference between these different types? Size. That's it. Memory is memory from a coding point of view. Some memory behaves differently than other memory. So we might choose to use certain kinds of memory for different purposes. Ultimately, we are storing bits inside of buckets of memory. What those buckets look like are up to how the human who writes the OS decides to, abstract that particular manager. So, for example, for our system memory, we have decided to abstract system memory to be a bunch of 1 byte buckets of memory. We have decided to abstract the idea of a memory address to be 4 bytes. We decided that. So we decided that what system memory looks like is a bunch of 1 byte buckets. And then we decided that we would use 4 byte memory addresses to be able to count that high. Because what is a memory address? I know I'm going to go a little bit over, but I want to make sure we get this thought all the way out. So if you need to go, I'll keep the recording going. So what is the purpose of a memory address? It allows us to index a specific place in a memory abstraction. What does this ultimately mean? If I have memory address 0004. So this is 0 by, so this is a 4-byte memory address. Actually, it's not. That's a 4-byte memory address. This is a byte, this is a byte, this is a byte. So if I have memory address 4, and I visualize my memory as being a bunch of byte size, basically being a byte size array, this is bucket number 4 in memory, where memory is divided into byte-sized buckets. So this is byte 4 in total memory, as an example. We chose that. We decided to say system memory was a gigantic array with resolution of 1 byte per bucket. We could have chosen to have it be 14 bytes per bucket, for all I care. But by doing that, we would have had more internal fragmentation that we talked about last time, where we'd had wasted memory. Now we have complete control over all of our RAM, in that our RAM is broken down into the byte level. And the reason we chose byte and not bit is because we don't have a data type in C to represent bits. The smallest we have is bytes. All right, and so, and we're doing them through chars because that's what a char type is, a byte big. All right, so don't get too hung up on the word char. It's a 1-byte data type called a char. Could be called a donkey or an elephant or something like that. Doesn't matter. Or LOL. It's a data type that's size 8 bits, size of a byte. All right, so since we have decided as the operating system writer to treat our system memory as being a giant array where each bucket is a step of size 1 byte through memory, that means for 32 megabytes, so 32 times 1024 is kilobytes times 1024 is bytes. This is the number of total buckets, total byte-sized buckets of memory we have in our 32 megabytes of system memory. We have 33,554,432 buckets of 1 byte memory. And in order to represent a value that large, in order to count that high, we need 4 bytes of memory. Our memory addresses, we can't count this high with a 16-bit memory address. 16-bit only lets us count up to 65,536. That's less than this. 32-bit memory address, or a 4-byte memory address, will let us count up to 2 or 4 billion, depending on if it's signed or unsigned. A number that is bigger than this guy. 2 or 4 billion. I don't know, I might have said million, but 2 or 4 billion is 32 bits. So the only reason we chose a 32-bit memory address is because we needed to count at least this high in order to address this many 1-byte buckets of memory. And why are they 1-byte buckets of memory? Because we chose for them to be 1-byte buckets of memory. This is all consequences of our own decisions because we're writing the operating system. So what we actually can support is 2, go back here. So in our example, we're only supporting 32 megabytes, but we can support with 32 bits. This is 2 to the 32nd. That's the number of unique buckets. So if we assume it's an unsigned number, that is 0 to 4.294 billion. That is the number of bytes that we can now address. Since every bucket of our memory is 1 byte big. So that number there divided by 1024 is kilobytes, divided by 1024 is megabytes, divided by 1024 is gigabytes. So using a 32 bit memory address, we can have a maximum amount of system RAM with 1 byte resolution of 4 gigabytes. Using a 32-bit memory address, we can address up to 2 to the 32nd unique buckets of memory, which would give us 4 gigabytes of maximum addressable memory. If we went to a 64-bit memory address, 2 to the 64 divided by 1022 is, or 1024 is going to be kilobytes, megabytes, gigabytes, terabytes. So we can have 16, actually, I need to divide it by 2 terabytes of memory, because I had it in bits first with 64 bits. So if I decided to, instead of 32-bit memory addresses, use 64-bit memory addresses, that allows me to index more unique buckets of memory. And if I'm going to have my memory be 1 byte resolution, then I can have 2 terabytes of memory with a 64-bit memory address. Okay? The punchline of this, though, is that memory is memory. We think of it like an array. We access different buckets of that array. The more memory we have, the higher we have to be able to count, and our memory addresses need to allow us to count high enough. So if we only use a 1 byte memory address, we can only count to 256. If we use a 2 byte memory address, 16 bits, we can only count to 65,536. If we use a 4 byte, we can only count to 4 billion. If we use a 8 byte, we can count higher. If we use a 16 byte, we can count even higher, so on and so forth. We have chosen those memory address sizes to allow us to count high enough to talk about all the different buckets of memory. Whether we're dealing with system RAM, a register, a hard drive, or a DVD drive, these are all arrays of places to store things. How they're stored, the speed at which they're stored, and the speed at which we can talk to them might be different, but memory is memory. It's a bucket that can hold a value. And we've made the decision that the size of those values that it holds in a single bucket is 1 byte. And because of that, we have a lot of buckets, and we need at least 4 bytes to count high enough to reference all those buckets, to index all those buckets. Okay, questions about all that? Hopefully that brings the homework into even more clarity, but also connects the dots with our different types of memory being addressed the same way. They just happen to have different abilities, just like we use all sorts of vehicles to get us. If we wanted to go to the grocery store, we could ride a bicycle, we can drive a scooter, or we can drive a minivan, or we could drive a sports car. The sports car is like the register. It'll get us there the fastest, but it might be the smallest to fit in, at least for somebody my size. But you get the point. We have different options. They all will let us travel from point A to point B. Just the speed by which we travel might be different. All right, so questions? Going once. Going twice. All right. So I will see everybody on Monday, normal scheduled time, when the homework is due. We'll talk more about the file system then and what things we need to be able to do with our file system, which is just a new way of handling memory, probably bigger memory, that we're going to assume is going to be slower memory. Also, if you didn't notice on Slack, I did announce the senior seminar presentations. I gave you the dates and who's presenting at what time. I'd appreciate if you save that date and time on your calendar to attend the Zoom meeting for that and support the seniors. It's going to be the Tuesday and the Wednesday night prior to finals week. So the last normal week of the semester on Tuesday and Wednesday night. I'm not requiring it in my classes. You won't get extra credit for it, but I will look down upon you if you don't show up. So you can decide if you want to, incur my wrath, I suppose. So unless you have a good excuse, like you have another class, you have work or something like that, I expect everybody to be there, and I'll be disappointed if you're not. So I will see everybody on Monday. I'll hang out for a couple minutes if anybody has any specific.
Can you stare at my
No.
homework real
No.
quick, please?
No.
Yes.
I said no.
I said yes, you should.
Why can't you figure out your own homework?